How can students truly understand energy transformation in a pendulum without needing complex lab tools? We developed an interactive web-based simulation to help students visualize mechanical energy transformation in real time. Mechanical energy, which consists of potential and kinetic energy, is often difficult to grasp in abstract form. Traditional teaching methods don't always help students connect theory with reality. That's why we built a web-based simulation that is interactive, flexible, and accessible, enabling students to see how energy works in a pendulum system. The goal to improve understanding and engagement to dynamic visualization and direct manipulation of physical parameters. In a pendulum, energy transforms periodically. Maximum potential energy occurs at the highest point. Maximum kinetic energy occurs at the lowest point. In an ideal system without external forces, the total mechanical energy remains constant. This is known as the law of conservation of mechanical energy. This simulation is designed to demonstrate this concept visually and interactively. We developed the simulation using Python and Place for the backend and HTML, CSS, and JavaScript for the user interface. The development process followed 5 stages. There are needs analysis, interface design, programming, internal testing, and evaluation. The goal was to create a digital learning tool that is functional, user-friendly, and physically accurate. The simulation features are a pendulum animation that moves based on user-defined parameters, a control panel to adjust string length, mass, initial angle, and gravity. Energy graphs displaying potential, kinetic, and total energy over time, an angle versus time graph showing oscillation patterns. Real-time data such as angular velocity, energy values, and period are also displayed. An export to CSV feature allows users to download data for further analysis. The simulation supports experiment under different gravitational settings, Earth, Moon, or Jupiter, demonstrating how environmental factors affect motion and energy. Internal testing showed that the simulation runs smoothly with a clean and informative interface. The energy graphs are consistent with theoretical models of the ideal pendulum. Total energy remains constant in the absence of damping, and the energy graphs display clear sinusoidal pattern, high contact colors, interactive colors, and real-time data displays help users understand the relationship between motion and energy. This simulation has not yet been tested directly with students or teachers. Future development should include user trials to evaluate its real-world effectiveness in education. Adding non-conservative forces like air resistance would also make the simulation more realistic. Through this web-based approach, learning physics becomes more interactive, exploratory, and enjoyable. Let's learn mechanical energy, not just to formulas, but to engaging, accessible visual experiences for